Yeah, I actually did a lot of things somewhere between math and physics or computer science, and now that I feel like I'm getting older, I'm moving more towards physics and experiments and so on. So at least I like to see something that really works in the lab. And so I hope that what I'm going to talk to you about today is not unrealistic in that respect. So what I'm going to talk about is based on two papers that we just put out. Actually, one was last year, and the other one was fairly recent. And it's about encoding a qubit in an oscillator. And it's basically, so what I'm going to cover is basically, well, a little bit of a background. What kind of ways, do people put qubits in oscillators right now, in particular with superconducting qubits and the circuit-QED paradigm. And I think you probably have heard things about that from the people who do this themselves, the people at Yale. And basically the scheme that I'm going to be discussing is like sort of one step further into that direction. And I hope that it's experimentally feasible as the CAT states that are prepared right now in oscillators in their lab. But so the scheme that I'm going to discuss is a scheme that was proposed by Gottesman, Kitaev and Preskil in 2000, so a while ago. And I claim that it's been kind of dormant since then. And there's a good reason that it's dormant, because many people thought this is completely unrealistic. You can't do this. It's too hard. And there was also not a good way of realizing the qubit state that this scheme proposed. And so our insight is that we actually have a way of preparing these qubit states. And it's actually not potentially that hard, in particular if you have the beautiful hardware of circuit-QED. And then the second part of the talk is on also using this idea of Gottesman, Preskil, Kitaev in a different way as preparing a state that can be looked at as a sensor. And I think that is a new insight into this paper that I actually will try to introduce by asking you a question and ask you what you believe is the case. And then maybe if you all say, no, it's impossible, then I say, yes, it is impossible, and here is how it goes. Okay, so why would we want to encode a qubit in an oscillator? And I mean encode a qubit in an oscillator. We just want to take two states in this oscillator, and one we call 0, the other one we call 1. And we'd like to choose our 0 and 1, of course, such that they're well protected. That to say they are long-lived states. Any superposition of them should be long-lived. And so, you could take the vacuum and a state with a single photon, but that may not be the best way of preparing a state. Also, it may be hard to drive transitions, as people have conventionally said. So if you talk about protection, you also have to discuss, of course, okay, so how do errors, photon loss, nonlinear interactions, other couplings to the environment, how do they affect these states, and how do actually reverse the noise that these states may feel? So how do I do quantum error correction? Now, a scheme that's currently being explored in the lab is, I would call, and it's being referred to as a CAT code. And so for this CAT code, we can take the state 0 to be a superposition of two coherent states, alpha and minus alpha. So alpha and minus alpha being sufficiently far, say they have 2 or more photons, such that they are orthogonal. And then the state 1 is I alpha plus minus I alpha, another CAT state. And the idea is that these are approximately orthogonal if alpha is large enough. And why would one want to do that? Well, a fact is that if you have a single photon loss, so look at the operator, annihilation operator A, what it does on these two states, these states are actually states of even number of photons. A single photon loss makes it a state with an odd number of photons. And actually A on 0 goes to this state. No? So what you'd like to do is you'd like to do a measurement that determines the parity of the number of photons. A measurement that does not distinguish 0 from 1, right? Because that would be decoherent these states. but just determining whether the parity has changed. And that's basically, and I'm not going to go into much detail, that's basically what they're doing now in experiments by the Yale group, which are really, at least they claim, and I think there's some truth to that, this first type of experiments in which you extend the lifetime of a qubit by active error correction, by actively measuring the parity of the state and see how it changes in time. And the workhorse behind this type of, so they prepare these states in a cavity. So it's the oscillator is represented by a single cavity mode that has a very long lifetime of a 3D cavity. And they do this, the preparation of the state and this measuring of this parity happens by coupling this cavity mode to a transmon qubit and using a dispersive interaction. So that's the workhorse which allows them to do these kind of things. Of course, very much summarizing what they do. Okay? So now let's go one step further and let's look at this protocol described by Gottesman, Kitaev, Preskil in 2001. And so they described a fictitious state, I would say, and the description of the state is as follows. Okay, so it's important to sort of understand the gist of it. So I have two operators. One I call SP, and this is momentum operator P. It's dimensionless, and Q, I have also Q, it's also dimensionless. They obey, so like you could think about as quadrature operators. They obey the usual commutation relations. And of course, I cannot create an eigenstate of P and Q simultaneously. But, and this is a very nice insight, I can create an eigenstate of, common eigenstate of two functions of P and Q. Functions being like this. I have this function of P, this function of Q, and this operator SP and SQ are commuting. Why are they commuting? Well, it's because if you look at two operators like that, either the A, either the B, and A and B are linear combinations of P's and Q's, then you can check the commutivity with this, and you have a phase factor, either the A, a commutator A with B, and it turns out by this choice of these parameters, this phase factor, as you see, is 4 times pi, no? Yeah, which is, of course, then 1. Oh, so the thing is that by choosing, so you can also choose other parameters. Instead of having this 2 times the square root of pi, you could have this alpha, and then this is also something divided by alpha. You know, there's other choices by which you can have this phase factor to be 1. Yeah? So there is potentially states that are eigenstates of these two operators. Now let's look at eigenstates with which the eigenvalue is +1. Now the eigenvalue of this has to be +1. What does it mean for P? Yeah? It means that P is 0 modulo square root of pi. So it's 0, it's square root of pi, 2 square root of pi, minus square root of pi, yeah. Just integers times square root of pi, and the same with Q. Now, it turns out that this choice of these two operators does not fix a single state, but it fixes a subspace, a two-dimensional subspace, because we can find two more operators, which we call Z and X, being poly Z and poly X on our qubit, and that also commute with these operators. So for example, this one, it's just the square root of this SQ operator. And you see that if I have a state which is also a +1 eigenstate of this operator, then Q has to be an even multiple of square root of pi. No? And if it's a state which has -1 eigenvalue with respect to this operator Z, it has to be a state which has for which Q has odd multiples of square root of pi. No? And a similar thing can be said about the X operator, but then you go to the Hadamard rotated basis. Okay, so this is important. So these are interesting states, but they're very unphysical, because what they are is, let's see, if I have a state, for example, the 0, what would it be? It's uniform superposition over, if as a wave function in Q, it's a uniform superposition over delta peaks at position 0, 2 times square root of pi, 4 times square root of pi, etc. And you know that, of course, one peak already at some Q is an infinitely squeezed state. So the idea that you can create a grid of such delta functions, or a sum of these delta functions, does not look very physical. Okay, so the question is, what about, and this type of state has an infinite number of photons, because it requires infinite squeeze. So what about a finite photon number version of these states? So the main question which we solve in our work is how to actually prepare a finite photon number version of these states using a nonlinearity, using a coupling of the oscillator with a qubit. Another qubit which is used to put the state of the cavity mode or of the oscillator in this type of state. Okay, so a finite photon number version of these states will not be a sum of an infinite sum of these peaks. It will be a sum sort of like this. This is the wave function of the zero state for a certain number of photons. So the idea is there are peaks at even multiples of square root of pi. But there is a finite envelope, a Gaussian envelope, and these peaks are not infinitely sharp. So there's finite squeezing involved. And similarly, it has peaks at odd multiples of square root of pi. Now, why do these states, what is the motivation behind these states? Well, let's look at these two wave functions and imagine small displacements having, or shifts in Q. So a small displacement generated by the operator P will shift this peaks slightly to the left or to the right. The idea is that if that shift is small, that's to say if it shifts by square root of pi, I get the state 1, right? That's a big shift in my formalism. If it shifts by less than half, the idea is that I can correct it, because if it shifts by less than half, it's clear sort of where it's from, and I can undo this type of error. At least if I do the right measurement that detects that, which is non-trivial. But the idea is that this type of code, this type of state, you are protected, or it's meant to detect and correct small displacements. So you see that for the wave function in Q this way, but the idea is that if you look at P space, the wave functions look similarly. So also you are protected against small displacements in the other quadrature. Okay, so these states are also called grid states. Now, if you're familiar with Wigner function, I'm actually not going to go into details here. This is an idea of the Wigner function. So it has this pattern, so it's sort of a grid. These points are on the grid. I don't actually want to go into it here. Now, when I talk about these states to other people, one of the things that I think is the hardest to understand is, or the question I always get is, well, displacement errors, fine, but I have a cavity mode, and the predominant source of noise is photon loss. How do these states deal with photon loss? And this is actually not so easy to explain. They do deal with photon loss, but it's not so easy to explain. And that is why, and there actually are some new results on how well they do this, but I can only make a mathematical statement which may be unsatisfactory to some of you, okay? And the mathematical statement goes like this. You have to think about displacement as a basis of errors, like Pauli errors are a basis of error on qubits. It doesn't mean that they are the predominant source of decoherence, right? Relaxation, amplitude damping is a more natural noise model. But the idea is that you can expand any type of errors as a linear combination of Pauli errors. So similarly, any type of operator on this oscillator, be it the annihilation operator A, can be expanded in terms of linear combinations and products of displacements, yeah, for any real u and v. But now I said before, if the displacements u and v are small, so if they're smaller than the square root of pi over 2, I claim that the code can correct this. So what I have to show is that dominant source of loss, photon loss at low rate, can be expanded in terms of displacements for which these u and v are small. Now, if you think about what that means, this depends, whether it's true depends on the number of photons that I have in my oscillator, right? Because let's imagine I have a, let's imagine I have a coherent state. Let's imagine, because the claim is that I want to, maybe I have in my oscillator, I have photon loss, but I may also have other things. For example, I may have a small over-rotation on my state, and I don't quite know what theta is. Well, now, it's clear that if I have a coherent state, which is sort of out here, and I have some small rotation, now it goes to there, say theta is small, small theta. If I want to write such operation as a linear combination of displacements, which are translations, I need at least displacements that are of this size. Yeah? Otherwise, I'll never get this state to over there. Yeah? But for that reason, if I would have the coherent state out here, people can't see this on the other side, have it a much larger coherent state, of course, a very small rotation induces a big translation. Yeah? So you cannot claim that such, even if theta is very small, if your number of photons in your oscillator is very large, you cannot expand this in terms of very, very small displacements. Huh? So this type of so it says that it never pays for these states to go to very, very large photon number. There will be some photon number that's optimal or maybe experimentally feasible, by which you have to work. So you always have to assume that there's a maximum number of photon numbers in the oscillator. And then you have, say, an operator like this. Maybe that comes out of some photon loss expansion of a Lindblad equation. There's some time scale, there's some kappa, some decay rate, and there's some powers. And you can, there are means, and we do this in the paper, to expand this in terms of small displacement, assuming that this kt times the square root of n max is much, much less than 1. Yeah? So you have to assume that the rate at which your noise happens is low compared with the number of photons. Otherwise, it's... and so the question, of course, is, are you in this regime? Yes?
So you're not necessarily saying that you can't come up with a scheme to protect against large n. You're just saying that this approximation doesn't work.
It
seems intuitive that large n.
Well, it depends on the rate at which the errors occur, right? So the point is that I always have to have some condition that the rate at which errors occur times the time scale that I'm interested in and times the photon, numbers the photon has, that has to be a small parameter. And if I'm in that regime, then I can expand, the processes that are involved with that in terms of small displacement. Maybe that doesn't answer your question. Okay.
Is this related to the square root of pi over 2 limitation?
No, the square, yeah, in some sense, yes.
The coherent state is big enough, then a tiny, for example, phase error would represent, well, I don't know.
Well, the tiny phase error would rotate the state over there, but this is not what I want, right? I want, it is related what you're saying to, the fact is that the code can only correct against small displacement. It's kind of saying that if I have many qubits and I put them in error correction code, I can correct against a few errors, yeah? Not against arbitrary errors, one error maybe. And here, that sort of being able to correct, now I can only correct against small displacements. Yeah? And the question is, is that a good set of errors? Now, I think I can mention one thing. There is work that is being prepared right now by the people at Yale, in which they look at this code in comparison with the CAD code and some other class of code, and they see numerically also that it corrects quite well against photon loss. For the lowest numbers of photons, the CAD code does better, but if you go to higher numbers of photons, but still, not like 100, but maybe, order 10, 20, then this code actually does very well. But it's not so easy to argue this, purely on mathematical grounds, because you need this expansion of errors in terms of small displacements. Okay, now, how to do error correction? Now, I want to mention two things. One is something that Knill and Glancy did in 2006 that uses, let's say I've prepared a state in an oscillator that I want to protect. Now I need to prepare another state, a similar state in another oscillator, and I need to connect them on a beam splitter and do some squeezing. And then I can correct this state. I can correct for the displacements that may have happened. And so that's one scheme of doing error correction. And there is some threshold below which this works, but I don't really want to say too much about it. What I'm proposing as error correction is actually using the same thing that is used to prepare a 0 or a 1, which we'll see in a moment. Are there questions right now about? Okay, so a few words about the circuit-QED paradigm in the sense of what kind of tools I'm invoking. Because if you say, well, can we do this in ion traps or nanomechanical oscillators? There's oscillators are all around us. Now, in general, this will be hard because the circuit-QED paradigm, as you probably know, is very powerful in the sense that one has high IQ microwave cavities, say 1 millisecond or higher. We can couple them these high-quality qubits, which have at least 10 microsecond coherence times. There's a strong dispersive cavity-qubit interaction, which this is the workhorse in our protocol also, having an interaction between the qubit and the cavity that looks like that. And so the point is that what we really like to do is to have a scheme that we can really do with the circuit-QED. And we want to have a scheme where we use no more than 50 photons. And that's already high, although they have experiments where they say I put 100 photon CAD state, but it's quite hard to get there. Yeah? Now, one thing I'd like to note is that if I have this interaction, so there's a qubit, like a transmon qubit, that's coupled to the cavity via this interaction, I can use that to do these types of rotations. So there are qubit-dependent rotations on the cavity. If the qubit's 0, you rotate this way. If the qubit's 1, you rotate that way. And you can also do that to do a qubit-controlled displacement. There are other ways to do a qubit-controlled displacement, and that's actually this little circuit. So there is what is a qubit-controlled displacement? If the qubit is 0, I do not displace the cavity. If the qubit is 1, I displace the cavity with some displacement operator d alpha. And that can be done by using controlled rotations and displacements that do not depend on the qubit state. And so controlled rotations in this type of circuit take 200 nanoseconds, which is quite a bit less than these numbers. Okay, so the preparation scheme that we'll propose is something where you start with a squeezed vacuum in this cavity. And then you'd like to have a series of transmon qubits coupled to the cavity and being measured. So a qubit is put in a plus state, it interacts with the cavity, maybe you do some displacement, you do some single qubit gate, you measure the qubit. Next qubit is done. So we'd like to do that like 4 times, 6 times. We have a protocol where it happens it happens 8 times. The more times you do it, the better the state you get, assuming for the moment there's no other sources of noise. Okay, so now I want to, so why is that a good way of preparing these states? Yeah? Okay, so what I want to do is I could say I have two operators, SQ and SP, these two. And I just want to create an eigenstate of these operators. No? Now, it's actually not so hard to be already an eigenstate of this operator, because I can prepare a squeezed vacuum such that Q is approximately 0. Of course, it's never perfectly true, so there's some error on this, which is fine. Yeah? And so I'm done with that operator. Now, I would like that state, that squeezed vacuum state, I'd like to, in additionally, project it onto an eigenstate of this operator. Now, this operator commutes, so the fact that I have already an eigenstate of the other is fine, it's not changed. Now, so what do I have to do? Well, how do I project something on an eigenstate of a unitary operator? I have to measure the eigenvalue of the operator. It's some unitary operator, it's e to the I theta. And if I know it's e to the I theta, I can either do a displacement such that theta is 0, so I'm a +1 eigenstate, or I can just say, okay, I work with an eigenstate for which the eigenvalue here is e to the I theta. That's also okay. So I have to do something which we know very well. It's called phase estimation of a unitary operator. And so then, and you say, well, how do you do phase estimation? Well, the workhorse of any phase estimation, so if I have a unitary operator U, and so I have a so this is the authority. So I have a unitary operator U, and I want to, it has some, I want to, basically, I don't want to estimate its phase, I want to project it onto an eigenstate with a certain eigenvalue. And I only can do this approximately. And the typical way you do this in the factoring algorithm or other means, you use circuits which use this tool, U to the K. So I have a qubit that starts in a plus. I do some U to the K. I may do some other qubit rotation, and I measure the qubit in the plus-minus basis, and I repeat something like that. And every time I do such a circuit, I get one bit that tells me something about this phase. And I do this repeatedly. Yeah, I have this cavity state. I do this circuit, outgoing cavity state. Next qubit comes by, takes that outgoing cavity state, does that, the same thing. And K can typically be varied. But K here, what is U here? U is a displacement. So if I were to choose a very large K, I have to do a very big displacement. For example, in the factoring algorithm, you use this K actually scales like, it's something that scales like 2 to the K. If you do so that's a not very useful way of using photons, because the bigger displacement I do, the bigger the number of photons. So we looked at the standard textbook phase estimation, and the first protocol you can look at already has 100 photons, so, you know, that's too much. Okay? So we look at some other things. So they're also, so actually the circuit that we use is something like this. We don't do, so we start with a squeezed vacuum state, and then we apply this circuit M rounds on the same cavity state, right? These things that comes out goes back in the next circuit. So this is a storage cavity. We have our transmon qubits, put in a plus state. We have to do controlled displacement. This is something to symmetrically place the state around the vacuum state. We do some, you know, single qubit rotation that can depend on previous qubit measurements, and we measure it in a plus-minus basis. And we do this M times. And then we say, how good a state do we prepare by this? How many photons do we use, and how good is this state? And there's two protocols, one in which these phases are preset. They're either 0 or pi/2, and we're not changing them. Then there's a protocol with feedback in which these phases are changed. Okay, so I want to mention, so I can just mention, so we've numerically simulated this, how well it does. So we start with a squeezed vacuum with 8.3 decibels of squeezing, and we take an MS8 protocol with the numbers I got from this circuit-QED that would run in 4 milliseconds, assuming that everything is done after each other, and a measurement takes 300 nanoseconds and so on. number of photons is about 25 with a large variance, because that's the frequency. And we get a good protocol. The problem is a little bit to say, well, how good is the state? This is hard to capture. Okay, so there's a measure. I actually don't want to go into this, but this is actually, if you look at the Wigner function, it looks like a good grid state. Okay, so now we also have some results about when photon loss happens during this scheme. It will deteriorate the quality of the prepared state, of course, but not in a way that it really washes out, maps 0 onto 1 or so. The biggest concern actually are the fact that there are nonlinearities in the Hamiltonian that couple the qubit to the cavity that we don't want to have there. So we either treat them as a source of displacement errors, and then they're actually a bad source of displacement errors, which may not surprise you because, of course, these terms scale with n squared, so their effect gets stronger the more photons you have. Yes, yeah.
So you have this kind of finite envelope for these combs that fall off. So what determines how wide this envelope is?
Well, the number of photons, it depends on the number of photons. Yeah.
I thought the number of photons determines the width of the...
Yeah, but it goes together. So the thing is, there is so GKP wrote down an approximate form of these states in which there's one parameter, delta, which determines the squeezing of the peaks and also the envelope. Because you'd like them to behave the same as in P and Q, because there's no reason why they would be... yeah, we know I think this, well, I don't know, the delta parameter doesn't say, but you know the relation between number of photons and this delta parameter.
So they're both determined basically by the dB of squeezing that you have?
Yes. I mean, we set the dB of squeezing such that what you get out, because in this protocol, you measure only one SP operator. The SQ, you're done with by the squeezing. So we'd like to get the quality in the SP and the SQ to be the same. So we take as much squeezing as such that this M is equal protocol gives a similar behavior. Okay, so now I'd like to switch. Okay, so this is something we propose, and we're still analyzing the noise during the protocol. And one thing is that what is nice about the scheme is that if you can make these states and stabilize them, so you kind of keep measuring this SP and SQ using phase estimation, because that's also doing your error correction, right? Because you just want these states to be eigenstates of SP and SQ. And as long as you know their eigenvalue approximately, you're good. And you can concatenate, you can concatenate, I mean, okay, one of the interesting things about these code words is that gates like the Hadamard gate on the 0, 1 is very simple. It's just actually, you have to move P into Q, so it's just waiting. The controlled NOT gate is linear optics. So you can also concatenate this scheme with the surface code. So you have one oscillator in which you create this state, and you keep on monitoring it. And now you have a grid of 2D grid of oscillators, and you can do a surface code in this way. So, okay, my point is, this scheme may have advantages over the CAD codes and some of the other codes that they have proposed in terms of scaling this up to larger systems and making it really fault tolerant. But I mean, the jury is still out. Okay, so let's now switch gears. So one thing, which in some sense is obvious if you know this grid state, but then on the other hand, it was not at all discussed. So what I'd like to look at is this problem. So now I don't want to encode a qubit in an oscillator. I want to prepare one sensor state in the oscillator. What's a sensor state? It should be a state that is sensitive to small displacements. Now, these displacements could be due to noise, and what you actually like is that, okay, there's little noise, so maybe small displacements are due to noise, but then there's also other, forces that you may detect by doing this, right? So larger, the time-dependent force that acts on the oscillator, still inducing a displacement that's small but larger than whatever background noise you have. Yeah? And you would like to measure properties of this force. Yeah? So the displacement, because displacement is characterized by two parameters, right? We don't know where displacement goes in that direction or that direction. So, you know, it's a real part of beta and an imaginary part of beta, or there's a u and v. Yeah? And now the goal is that, so we've prepared my sensor state. A displacement acts with some parameters u and v that I don't know, and assuming other source of noise, and this displacement is due to some time-dependent force. U and v are small, and the goal is to estimate what u and v are in order to derive what the force is. Yeah? And so I want to do that with a single measurement. And now the question is it possible to get the accuracy? So you see u is associated with, you know, p, and v is associated with q. Is it possible to estimate u and v as some u tilde and v tilde by a single measurement with, say, such that the variance of this u tilde and v tilde is very small? The accuracy with which I estimate u and v can be arbitrarily small, but for both parameters. I just want to do one measurement and get the accuracy in both parameters to be 0. Because it looks like this may be forbidden by Heisenberg uncertainty, right? Because I certainly, you know, I cannot measure p and q simultaneously. So if I were to do something like that in order to measure this small shift, that's not the way to go. No? But here's where these states come in. Okay, I can't create an eigenstate of p and q simultaneously, but hey, I have actually created an eigenstate of p and q modulo something simultaneously, right? So and if these displacements are small, they just, you know, they will shift these eigenvalues of these two operators slightly. But these are commuting operators. Yeah. Now, what I find interesting is that so when I was looking at this, I read a paper, or was looking at a paper, Reviews of Modern Physics by Caves and Thorne and other people about limits. This is about a force coupled to an oscillator. What are the fundamental limits? They don't say this. They actually say you can't estimate amplitude and phase simultaneously with high accuracy, right? Because of Heisenberg uncertainty. And I don't claim that they're wrong because I haven't read the whole paper, but I think this is something that has been missed, that if your displacements are very small, it's only for very small displacement, you can in principle get this accuracy down if you increase the number of photons in the state. This is what the figure of merit is. Of course, like I said before, you can't have an arbitrary number of photons. Okay, but it's not forbidden. That's the point. Okay, so what can we do? So the grid state achieves actually this. So now we only want one state, right? I don't want a 2-qubit space, so I can say, well, okay, I take a slightly modified version of these. I have these two operators, they're the same. And again, they commute, because it's the square root of pi. And so I have a state which is, you know, p and q are multiples of square root of pi. So this is a state that's created by one of our protocols, for example. This m is 8. Okay, now, of course, people have written endless papers about estimating parameters. And actually, every day there is a paper on estimation theory on the archive. No, so let's put it into that context. But usually the thing is that you estimate one parameter. And now I say I have to do a single measurement, I estimate two parameters. Now, what is the figure of merit? Well, I could say I look at the variance. What am I doing? No, it's kind of stuck on it. Yeah. I look at the sum of the variances. Yeah? And I want to get that to be very, very small. And I really want to do that with the measurement. Now, you can show that there is some math you can do which shows that the sum of the variance is lower bound by the trace of the inverse of a matrix, and that's called the Fisher matrix. Usually Fisher information is a single quantity. This is the quantum Fisher information. But in this case, it's a matrix, and it involves the variances of the operators p and q and also a covariance. And you can also show that if you say, well, how small can this be? This thing on the right-hand side. In principle, it can be as low as this quantity. But then you can ask, well, it's an inequality. So first, can it be tight? Maybe it's just a very weak bound. Yeah. Now, and I believe actually this cannot be tight, not for a single mode, but you can show this. Okay. So the sum of the variances for any coherent thermal or squeeze states or any Gaussian state is at least 2. This has been shown, just apply. And the idea is, of course, that, if you have a coherent state and the displacement's big, it's easy to distinguish, right? But the point is now I'm talking about displacements that are very tiny, such that the shot noise in the coherent state prevents you from getting a very accurate measurement. And see, the point is that with the grid state, if you let the number of photons increase, you get a very fine distinction. You resolve the phases, and that's why you resolve the displacement with increasing accuracy, no matter how small they are. Whereas for a coherent state, you cannot resolve this because of the shot noise. Now, what about a squeeze state? You say, well, if the displacement acts in this direction, I'll prepare a squeeze state like this, such that I really get very high accuracy that way, right? Because I have very, very small shot noise in that direction. But I don't know that the displacement acts in that direction. It could be acting in that direction. So it's clear I don't know how to choose my squeeze state to, optimally do this, right? Because the point is I want to estimate both these parameters. So this is why a squeeze state in this bound does not do better, because it's the sum of the variances. Now, one other state is where you say, okay, well, let's take a 2-mode squeeze state. 2 arms, 2 modes, one undergoing the displacement. Now, of course, the 2-mode squeeze state is kind of an eigenstate of the sum of the position and the momenta. So there again, you actually, and they showed also there, sorry, I should have added a reference, but the reference in our paper, you can show that you get actually this behavior. And you get that by a homodynamic measurement on both the 2 modes. And this is the base of, the 2-mode squeeze is used for superdense coding. I don't know if you're familiar with this, where you say, I want to, Alice has a displacement, the parameter in displacement, they share a 2-mode squeeze state. She does the displacement in her mode, sends her mode to Bob, and he finds out all the information about the displacement. Okay, so now our result, if you look at the grid state, which you prepare using phase estimation, and then you measure the displacement after phase estimation for both these two operators, you get something like this, 1 over the square root of n. So the point here is that people have focused, say, well, you can't, this is like the best for Gaussian states, and this bound, this Kramer-Rao bound, you probably can't achieve, end of story. Yeah? But that's not, there is room for doing something non-trivial here. Okay, but of course, in practice, I've also said that you always have to have an upper bound and a number of photons and so on. So in practice, you can still ask how good, how useful this is. Okay, so now one thing I want to comment on is, so because this came about actually from discussing also with Shulkov about what about the quantum compass state. So they have. You can create a superposition of 0 and 1. And so Zurek in 2001, he called this the quantum compass state. So I have a superposition of alpha, I alpha, and minus I alpha, like a compass, pointing in the 4 directions. And what he observed, so basically what he observed, he said, well, if I look at the Wigner function, then in this middle area, there are very small tiles in which the Wigner function switches from being very positive to negative, to this sort of very positive tile and then a negative tile. And the size of these tiles, the scale is like 1 over n, the number of photons. So he said this is phase space structure, which is arbitrarily fine if I let the number of photons increase. So this state is very sensitive to displacements, right? If I have a displacement of this strength, I can get this negative tile to a positive tile, and I can get a big change in my state. So I can actually, there's a little analysis that shows if you have a certain displacement of this strength, you can map it onto orthogonal state. So that was his point, that even though this, this is not such a weird state, you have this very fine phase space structure, and so this being picked up, this may be useful as a displacement sensor. Yeah? So I agree that it's very sensitive, but we also want to understand how does it compare with the grid state. Because sensitivity is not the whole story. So we did this game. We say, okay, and this is maybe a bit set up. We say, let's imagine there's a displacement that comes in, and these parameters are u and v, and I don't know what they are. They're uniformly distributed over a small interval, and it's, of course, precisely this interval in which this grid state can, detect these u and v. Yeah? And then, so then you get some state, and you want to determine what, you want to do a measurement, and you want to determine maximal information about u and v. Yeah? So this is slightly different as before, because now I have an a priori probability distribution of my u and v. And I'm asking about how much information is there in the state about this u and v. And then you can show that this, if you in that setup, the quantum compass state will have constant amount of information about this u and v, meaning that it does not increase with photon number. And this is not so surprising because, the point of Zurich was only that there is this very sensitivity for very small u and v. But if u and v is larger, I'm probably mapping this onto a fairly non-orthogonal state, and I cannot distinguish this so well. No? Whereas for the grid states, if I choose, of course, favorably these u and v in this interval, if I have increasing number of photons, I've increased resolution for all these u's and v's, and my information about the u and v increases with photon number. And so this is what we could calculate. There's the accessible information by the quantum measurement with phase estimation in the grid state increases with photon number in this following fashion. Okay, so that's, okay, so what I hope is that this grid state or modifications thereof, this is the eigenstates of P and Q. Maybe you can also do something with photon number and phase. There's some discussions about that. I hope that they may be experimentally feasible. I think this will be very challenging. And maybe there are even applications that do not, that are of interest for displacement sensing. So, let's see.
Phil didn't ask as many questions this time.